In this video, we're going to look at the chi-squared test for independence. And before we get started, we should talk about when you're going to be using the chi-squared test for independence, so you know if this video is even useful for you or if you need to go into something different. So the chi-squared test for independence will be used when I'm classifying some data by two attributes. So some examples of that are asking a group of students whether they prefer red or blue, then grouping them into females who prefer blue, females who prefer red, males who prefer blue, and males who prefer red. We can use the chi-squared test to determine whether the gender affects color preference. So one attribute is gender, other attribute is color preference. I could also survey people of various nationalities about their music preference and use the chi-squared test to determine whether nationality affects music preference. So the two attributes here are nationality and music preference. If you are trying to find a chi-squared video for goodness of fit, where I have sort of a multinomial thing I'm classifying in one way, that would be a goodness of fit test. There's a link to a video I made on that in the description down below. Also, if you want to skip ahead, if you see some things, or you don't want sort of all the explanation, there will be links in the description down below to various points in this video. And just as a point of reference, this first one here is going to be example 1. This second one here is going to be example 2. And I'll show you how to do it by hand and by the calculator, which is much quicker and easier, but maybe doesn't explain what's happening so much. So, onward. How do we calculate the chi-squared value? The first thing I need to do is collect all the data. And again, I'm going to put this in a matrix. So I have these two, I have the two coordinates, sort of row 1, column 1, row 1, column 2, all the way to the jth row and kth column. Then I'm going to calculate the expected numbers in the matrix, and that's going to be the sum of row 1 times the sum of column 1 over total, the sum of row 1 times the sum of column 2 over the total. And I guess the explanation for this is the following. So let me talk about this briefly. If they are truly independent, that means that the conditional probability does not change. So I have my chart, and I have sort of a few things here. So A, B, C, 1, 2. If there are, let's say, X elements that chose B, either in 1 or 2, and Y elements that chose 1, either in A, B, or C, and I have this total over here, what this independence says is I have a Y over the total probability of choosing 1 randomly for everybody, and if it's independent, then I should have the same probability there, so there should be X times that here. And that's just a way to actually find it. So I do the sum times the sum divided by the total. And we'll see it in the example. If that didn't make much sense, it's not hard to do, but that's why we're doing it. And then I just take all of the observed values that I collected, all of the expected values that I calculated, subtract them, square them, and divide it by the expected value. So this is basically how I do it. It's not hard, it's just time-consuming to do by hand. How do we interpret the results? Well, to interpret the results, we determine the degrees of freedom, which will be rows minus 1 times columns minus 1. The reason for this is the following. So if I have my table, and I'll just set this up again, A, B, C, 1 and 2. In order to make the expected values, I have to know, and let's say that there were 100 respondents in A, and 200 respondents in B. And let's just say that there were 70, response for 1, response for 2, 70 respondents for A. Let's do 130 respondents for B and 100 respondents for C. So these are the totals. I used all of these, so 300 total, to actually construct the expected values. And so there really are only, in this case, 2 degrees of freedom. Let's just say that I know that 40 people responded A1 and 50 people responded B1. The rest is actually determined. So if this is 40, this is 50, this has to be 10. If this is 40, this has to be 30. 50, then this has to be 80. And either way I look at this, 30 plus 80 gives me 110. This has to be 90. And you see the only things that had any type of freedom were these two. If this, instead of being 50, was 49, I could solve for the rest. So that's why I do rows minus 1 and columns minus 1. There are only actually that many free values in here. The rest are fixed, determined once you have those. Once I do that stuff, I'm going to look up a critical value in the chi-squared table. And the chi-squared table takes degrees of freedom and significance level. So here is a sort of snippet of a chi-squared table. You can look them up online. They're in the back of a lot of statistics books. The degrees of freedom go along here. So in that example I gave you, there were 2 degrees of freedom. And I choose a significance level. And, 1% would be 0.01, 5% would be 0.05, 10% would be 0.1. And the big goal of this, which is worth noting, is that I want to actually show that these things are dependent in many cases. When I do a study, it's far more interesting to me to show that 2 things are correlated, 2 things are affecting one another, as opposed to them being completely independent. And so once we get this critical value, I compare it to what we have. The null hypothesis is that they are, not a good approximation. I took this from Goodness of Fit, but that that the attributes are independent. And so if my chi-squared is low enough, then my values are close enough to the expected independent values, and so I will accept the null hypothesis. Now, that doesn't mean that's necessarily true. It just means it's not far enough off for me to say with any certainty that it's not true. However, if I'm far enough off, then I can show that they are not independent. Or in some way, they are dependent. And again, that's sort of my goal, is to show that we are farther off. So this 5% significance level actually means that there is only a 5% chance that the data itself is independent, but gives me data that's this far off of the expected. That's the idea. And again, 1% is an even stronger statement, saying there's only a 1% chance that I actually have something that is independent, but have been able to collect this data. So I hope that I am sort of outside of this in general. I want to show something interesting, but I can't guarantee that. Alright, now I apologize. Again, my error up here that I forgot to fix from my other video is going to jump right back in when I show the next slide. But in here, from the calculator, it actually gives us a p-value. And this p-value is basically, so p... I actually didn't change anything. Alright, so p is actually the probability that it is independent, but gives us results this, so I say bad, this far off. So a p-value of 1% means there's only a 1% chance that our data is actually coming from an independent set of random variable. Okay? Actually, calculating this by hand involves some calculus and integral of the probability density function. We will ignore that. We'll just have the magic p-value from the calculator. Okay, let's see some examples. So here's our first example. Ask 100 male students, 100 female students whether they prefer red or blue. The results are shown below. Use chi-squared test for independence with a significance level of 1% to determine whether color preference is independent of gender or not. So I guess I should notate this. My null hypothesis is going to be that gender and color preference are independent. They do not affect one another. And now I'll go through the process. So what I do is I add up each of the rows. 22 plus 78 is 100. 38 plus 62 is also 100. Shouldn't be surprised. I told you there were 100 of each. Add up each of the columns. 22 plus 38 is 60. 78 plus 62 is 140. I will also find the total. So if there are 100 females, 100 males, there are a total of 200 students in here. Or you could see if 60 people responded blue, 140 people responded red, then there are still 200 people. Now I do this process, and this is by hand the really annoying part. I need to find the expected values. And so what I'm going to do is this. I will take the row sum times the column sum. So I will do 100 times 60 divided by 200. And I will do 100 times 140 divided by 200. And I will do 100 times 60. So this is, row 2, column 1. I take row 2, 100. Column 1, 60, divided by the total 200. And I take, for this one, row 2, column 2, so 100 times 140, divided by 200. And this gives me the expected matrix of 30, 70, 30, and 70. Now I need to go through and actually calculate the chi-squared values. So I'm going to sort of do this in conjunction with the next slide. So my first, row 1, column 1, my observed was 22, my expected is 30, so I will do 22 minus 30 squared divided by 30, and calculating that out, that's going to equal 2.13 repeating. Now I go to row 1, column 2, and the actual order you do it in doesn't matter as long as I do all 4 of these elements here. So the observed was 78, the expected was 70, so I will do 78 minus 70 squared divided by 70, and that's going to give me approximately 0.914. And I continue. So row 2, column 1, observed was 38, expected was 30, so I will do 38 minus 30 squared over 30, which happens to give me the same value as this, so 2.13 repeating. And row 2, column 2, observed is 62, expected is 70, so I do 62 minus 70 squared over 70, which is also approximately 0.914. I add all of these up, so 2.13 repeating plus 0.914 plus 2.13 repeating plus 0.914. And this gives me an approximate calculated value of 6.095. Now, I don't know if using these rounded values get me there. I actually used all of the values in my calculator to get to this point. So if you are following along and just typing this in and get like 6.094, 6.096, it's just round off error. You didn't do anything wrong. You just sort of rounded too soon. So I guess that is wrong. Okay. So I have my calculated value. Now I need the degrees of freedom. Well, looking at this, I have 2 rows and 2 columns. So I will do 2 minus 1 for the rows times 2 minus 1 for the columns, and the degrees of freedom are 1. The significance level I want is 1%, so I'm going to use significance level of 0.01. I look this stuff up in the table, so 0.01 with 1 degree of freedom gives me 6.63 as my critical value. And so critical value 6.63. And now I can wrap this all up. So since my calculated chi-squared value, 6.095, is less than 6.63, my value is less than the critical value, we are going to accept the null hypothesis that gender and color preference are independent. Okay, now again, this doesn't sort of guarantee that they are. This is actually close to the critical value, but it's going to end up being about only sort of a 1 or 2% chance that it's independent and we get data that is this bad, but I'm not far enough off to reject their independence. Now let's look and see how to do this with the calculator. So going back to this, the calculator is really easy. I'm just going to put this into a matrix. So let me go into my calculator and go into the matrix. I'll put this into matrix A. It is a 2 by 2, so 2 by 2. And we have 22, 78, 38, and 62. And I don't need to put in the expected matrix. It's actually going to give it to me. So I'm going to quit out of here. Make sure I did it right. 22, 78, 38, 62. So quit. And then I go to stat, test. I just scroll my way down to the chi-squared test. There we go. My observed is in A. I will put the expected into B. I didn't need to actually program anything into B. And I'll calculate it. And there we have it, 6.095, which was the same that we got. It tells me the degrees of freedom are 1. And the probability is actually 0.0135. So the P will accept as long as we're above the significance level. The chi-squared will accept as long as we're below the critical value. All right. Second example, far more annoying. So, same process. First off, basically our null hypothesis is going to be that nationality and music preference are independent. I need to go through and find the expected values for each of these. So I find the sum. 53 plus 42 plus 61 plus 44 is 200. And just so you know, I actually did all these calculations before, so I'm just reading it off of my paper now. I'm not that fast. 30 plus 25 plus 29 plus 49 is 125. 51 plus 38 plus 43 plus 43 is 175. And finding the column sums. 53 plus 30 plus 51 is 134. 42 plus 25 plus 38 is 105. 61 plus 29 plus 43 is 133. And 44 plus 41 plus 43 is 128. I also need to find the total, so I add up all of these, and they both would give me 500. Okay, now in here I'm going to go a little bit faster. So I'm going to sort of fill out my expected matrix. And so to find the expected value here, I'm going to do 134 times 200 divided by 500. 134 times 200 divided by 500 gives me 53.6. To find out the expected value here, I'm going to do 105 times 200 divided by 500. 105 times 200 divided by 500 gives me 42. Keep on going. 133 times 200 divided by 500 gives me 53.2. 128 times 200 divided by 500 gives me 51.2. Next row, 134 times 125 divided by 500 gives me 33.5. 105 times 125 divided by 500 gives me 26.25. 133 times 125 divided by 500 gives me 33.25. 128 times 125 divided by 500 gives me 32. Final row, 134 times 175 divided by 500 gives me 46.9. 105 times 175 divided by 500 gives me 36.75. 133 times 175 divided by 500 gives me 46.55. And 128 times 175 divided by 500 gives me 44.8. So there's my expected matrix. Now I'm going to go through the same process. It's a little bit annoying, but I do the same thing I did before. So I'm going to do, for the first row, first column, observed is 53, expected is 53.6, so I will do 53 minus 53.6 squared divided by 53.6, which is approximately 0.0067. I continue. First row, second column, 42 is observed, 42 is expected, so I do 42 minus 42 squared over 42, which is 0. I continue. 61, 53.2, observed, expected. So I do 61 minus 53.2 squared divided by 53.2, and that is approximately 1.1436. I continue. Feel free to fast forward or skip on in the timestamp. So observed is 44, expected is 51.2, so I do 44 minus 51.2 squared over 51.2, and I get 1.0125. I continue. Observed is 30, expected is 33.5, so I do 30 minus 33.5 squared over 33.5, which is approximately 0.3657. Observed is 25, expected is 26.25, so I do 25 minus 26.25 squared over 26.25, which is approximately 0.0595. Observed is 29, expected is 33.25, so I do 29 minus 33.25 squared over 33.25, which is approximately 0.5432. Observed is 41, expected is 32, so I do 41 minus 32 squared over 32, which is approximately 2.531. It's exactly 2.53125, but I'm running out of space, and I continue. Observed is 51, expected is 46.9, so I do 51 minus 46.9 squared over 46.9, which is approximately 0.3584. Observed was 38, expected is 36.75, so I do 38 minus 36.75 squared over 36.75, which is approximately 0.0425. Observed is 43, expected is 46.55, so I do 43 minus 46.55 squared over 46.55, which is approximately 0.2707. And the final value here, observed is 43, expected is 44.8. So I do 43 minus 44.8 squared over 44.8, which is approximately 0.0723. All right, I add all these up. The sum is approximately 6.406. I look back at my table, my degrees of freedom. Well, I have 3 rows, 4 columns, so I do 3 minus 1 times 4 minus 1, which is 2 times 3, 6. My significance level, I want a 5% significance level, so I will do a significance level of 0.05. I look to my chart, and so here, let me change colors, I go to 0.05. With 6 degrees of freedom, the critical value here is 12.59. And so in here, since in this case, the calculated value, 6.406, is less than my critical value of 12.59, then we accept the null hypothesis that they are actually independent. Okay, so let's look at this problem one final time, this time using the calculator to see how much easier it is. So let me go to the calculator. I'll go to the matrix. I don't need to actually clear out the old matrices. I can just write over A, so I'll do that. I want it to be 3 by 4. And I just start entering stuff in. So let me do it with the keyboard, it'll be a little bit faster. So 53, 42, 61, 44. We have 30, 25, 29, 41, and we have 51, 38, 43, 43. Now, double check. I've messed this up a couple of times where I just had a wrong value in here. So 53, 42, 61, 44. And as you can see, I didn't type in 30. So let me get that in there, 30. If I had continued without checking, I would have gotten some wrong values, and I'd look awfully stupid. All right, the rest looks good. So I'm going to quit out of there, go to Stat, Test, go down to chi-squared test, or the observed is A. It doesn't matter, there's junk in B right now, it'll get cleared out. I'll calculate, and in here, so the degrees of freedom are 6. The chi-squared value is 6.406, which gives me a probability of 0.379, which is actually a very high probability. This one would say that there's a 38% chance or so that my data is this bad given an actually independent random variable. I hope this helped out. I know chi-squared can be a little bit of a trial and might be hard to find good information. Please feel free to comment below if you do have any questions. And yeah,